Across the galaxy, there are worlds that defy our most basic experience of time. Planets where the sun never moves. One hemisphere is forever scorched in the unrelenting glare of eternal daylight, a permanent global desert. The other side is a prisoner of physics, plunged into a perpetual frozen night, a realm of darkness that has not seen a dawn in billions of years. These are the tidally locked worlds, the most common type of potentially habitable planet in the universe. Tonight, our journey takes us to the far side of these planets, to the hemisphere of unending twilight and shadow. We will explore what happens when half a world is stolen from the light. We will witness storms of frozen air, descend through atmospheres lit only by starlight, and stand on the terminator line, the eternal border between day and night, where life might cling to a sliver of warmth. Prepare to venture into a realm of cosmic ice and shadow. To the night side of the tidally locked planets, we begin. Before we can journey into the darkness, we must first understand the force that creates it. It is a force we are intimately familiar with, yet its ultimate consequences are profoundly alien. It is the force of tides, the same force that pulls at Earth's oceans, but on a planetary scale, and enacted over geological time. It becomes a shackle, a gravitational chain that binds a planet's rotation to its star. This phenomenon is called tidal locking. The most perfect example in our own backyard is the relationship between the Earth and its moon. The moon always shows us the same face. We never see its far side from Earth. This is not a coincidence. The moon is tidally locked to the Earth. Its rotation period, the time it takes to spin once on its axis, is exactly the same as its orbital period, the time it takes to go around the Earth. To understand how this happens, imagine the moon in its distant past, when it was newly formed and spinning much faster. The Earth's immense gravity pulled on the moon, but it didn't pull on every part of the moon equally. It pulled harder on the near side than on the far side. This difference in gravitational pull created a slight bulge on both the near and far sides of the moon, elongating it into the shape of a football. Now, because the moon was spinning faster than it was orbiting, these tidal bulges were constantly moving across its surface. The Earth's gravity, however, was always trying to pull these bulges back into alignment. It was like a constant, gentle, but relentless tug on the off-center mass of the bulges. This created friction within the moon's interior, which acted as a brake. Think of it like a spinning tire that is out of balance. The wobble creates friction and drag, which slowly bleeds away the tire's rotational energy. Over millions of years, this gravitational brake slowed the moon's spin down and down and down until the braking force disappeared. The braking force only disappears when the spin is so slow that the bulges are no longer moving across the surface. This happens at the exact point when the moon's rotation period matches its orbital period. It has settled into the lowest energy state possible. It is locked. This same process happens with planets orbiting close to their stars. The most common type of star in the universe is the red dwarf. These stars are much smaller, cooler, and dimmer than our sun. For a planet to be warm enough for liquid water in a red dwarf system, it must orbit incredibly close to its star, often much closer than Mercury orbits our sun. At this proximity, the star's gravity is immense, and the tidal forces are titanic. A planet orbiting in the habitable zone of a red dwarf will inevitably become tidally locked, and it will happen fast, perhaps in just a few 100 million years. Its fate is sealed. One side will face the star forever, and the other will be cast into permanent night. This isn't a rare curiosity. It is likely the standard state for the majority of terrestrial rocky planets in the galaxy. A tidally locked planet is a world of two faces, a sphere of cosmic schizophrenia. It is not one environment, but two, each pushed to an unimaginable extreme. The two hemispheres, the day side and the night side, are as different as fire and ice, governed by diametrically opposed physical realities. Let's first consider the day side. Here at the substellar point, the spot on the surface where the star hangs forever motionless at the zenith, the nightmare of perpetual day unfolds. The ground is subject to a constant, unrelenting bombardment of radiation. There is no day-night cycle to provide relief, no evening to cool the scorched rock. The surface temperature can climb to terrifying heights, far hotter than any natural environment on Earth. On a planet like Proxima Centauri b, the surface could reach well over 100 degrees Celsius, or 212 degrees Fahrenheit, hot enough to boil water instantly. Any liquid water on this side of the planet would have vaporized into the atmosphere billions of years ago. The landscape would be a sterile, global desert. Chauve. The rock, baked for eons, would be fractured and brittle. With no water cycle, there is no erosion, so mountains would remain jagged and sharp, their peaks aimed at the star that never sets. The light itself would be different. Around a red dwarf, the light is shifted towards the red end of the spectrum. The sky would not be blue, but a perpetual, hazy, orange, or deep ochre. It would be a scene of profound desolation, a world cooked to death. Now let us journey to the other side of the planet, to the antistellar point, the center of the hemisphere of eternal night. Here, the opposite extreme reigns. The sun has not risen in billions of years, and it never will. The only light comes from the faint, cold glow of distant stars and galaxies, a light far too weak to provide any warmth. The primary source of energy here is the planet's own meager internal heat flowing from its core. The temperature plunges to depths that make Earth's polar regions seem balmy. We are talking about temperatures of minus 150 degrees Celsius or minus 240 degrees Fahrenheit, and even colder. Any atmosphere on this side would freeze. Carbon dioxide would precipitate out of the air as a dry ice snow. Water vapor, carried by winds from the day side, would instantly freeze into ice crystals and fall in a perpetual silent blizzard. Over geological time, this process would build up colossal glaciers, ice sheets that could be kilometers thick, burying the entire night side of the planet. It is a world entombed in ice. One planet, two hells. One side a furnace, the other a deep freeze. They are connected only by a thin shell of atmosphere and a narrow ring of twilight. And it is the behavior of that atmosphere that will determine the planet's ultimate fate. A world with one side superheated and the other side supercooled creates the most extreme temperature gradient imaginable. If the planet has a substantial atmosphere, that atmosphere will not remain static. It will be thrown into a state of constant violent motion. The atmosphere itself becomes a vast planetary-scale heat engine, desperately trying to achieve equilibrium by moving heat from the hot side to the cold side. The result is a weather system unlike anything in our solar system. On the day side, at the substellar point, the intense stellar radiation heats the atmosphere from above. The hot air expands and rises in a massive, powerful updraft. It's like a colossal, permanent hot air balloon, thousands of kilometers across, constantly lifting gas into the upper atmosphere. As this hot air rises, it creates a region of high pressure at altitude and leaves behind a region of low pressure on the surface. Meanwhile, on the frozen night side, the opposite is happening. The air, chilled by the eternal darkness, becomes incredibly dense and heavy. It sinks towards the surface in a massive planet-wide downdraft. This creates high pressure at the surface and low pressure at altitude. The universe abhors a pressure imbalance. Air will always flow from high pressure to low pressure. This sets up a simple, powerful, and relentless global circulation pattern. In the upper atmosphere, hot air from the dayside updraft flows outward in all directions, racing towards the night side. At the surface, cold, dense air from the night side flows back towards the dayside to fill the low-pressure void left by the rising air. The entire planet is locked in a single, massive convection cell. Think of it like a giant planetary air conditioning system, but one that is trying to heat a freezer. Hot air is piped from the furnace on the day side to the cryo chamber on the night side, while cold air is returned to be reheated. The winds generated by this process would be biblical in their scale and power. The winds at the surface, flowing from the night side to the day side, would be ferociously cold and constant. But the real violence would be in the upper atmosphere. Hot air, racing away from the substellar point, could reach speeds of hundreds or even thousands of kilometers per hour. These would be permanent, supersonic jet streams, far faster than any winds on Earth. The nature of this heat engine is the single most important factor determining the planet's climate. If the atmosphere is too thin, it cannot transport heat effectively. The day side will cook, and the night side will freeze, and the planet will be uninhabitable. But if the atmosphere is thick enough, perhaps as thick as Earth's or thicker, this global engine can move enough heat to moderate the extremes. It could keep the night side from freezing completely solid and keep the day side from boiling away its oceans. It is a desperate battle against physics, and the outcome of that battle is written in the winds. Between the furnace of eternal day and the freezer of eternal night lies a third realm, a narrow, permanent ring of twilight that encircles the entire planet. This is the terminator line, the boundary where light gives way to darkness. For any form of life that might exist on a tidally locked world, this sliver of perpetual dawn or dusk is likely the most precious real estate in the universe. Imagine standing on the terminator. A star would never rise or set. It would hang motionless, forever perched on the horizon. Half of the sky would be bathed in the dim reddish glow of the star, while the other half would be a deep, starry black. The light here is always angled, always soft. It is a world of infinitely long shadows, a landscape painted in the gentle, dramatic hues of a sunrise that will never arrive and a sunset that will never end. It is in this terminator zone that the conditions for life as we know it are most plausible. The temperature here is not extreme. It is a moderate average of the scorching day side and the frigid night side. Because the star is always on the horizon, the direct solar radiation is weak, but it is constant. This is the Goldilocks region of a tidally locked planet. If the planet has water, it is here in the temperate twilight of the terminator that it could exist in liquid form. We can envision rivers of meltwater flowing from the edge of the great nightside glaciers, winding their way through the twilight zone before evaporating in the hotter regions closer to the day side. These rivers would create deltas and shallow seas of liquid in an otherwise hostile world. The constant, powerful winds flowing from the cold side to the hot side would dominate the environment. Any life here would have to be adapted to a world of perpetual unidirectional wind. Plants, or their alien equivalents, would not track a moving sun. They would grow angled, permanently aimed towards the star fixed on the horizon. They might have dark reddish foliage to absorb as much energy as possible from the dim red dwarf star. Animals might huddle behind mountain ranges or in deep canyons seeking shelter from the relentless wind. The entire ecosystem would be aligned with this one, unmoving source of light and warmth. Civilization, if it were to arise, would be a culture of the twilight. Their architecture, their mythology, their very sense of direction would be defined by the fixed star and the river of wind. East would be the direction towards the star, towards the heat. West would be the direction of the killing cold, the great ice sheets of the night side. Their entire existence would be lived in this narrow, habitable ring, a planetary oasis nestled between two uninhabitable hells. The terminator is not just a line on a map, it is the potential cradle of life on the most common planets in the galaxy. While the terminator zone might offer a relative haven, the day side of a tidally locked planet could be home to the most violent and persistent weather feature imaginable. At the substellar point where the star's energy is most concentrated, the constant, powerful updraft of hot air can create something extraordinary, a permanent planet-sized hurricane. This is not a storm that forms, travels, and dissipates like the hurricanes on Earth. This is a stationary, self-sustaining vortex, locked in place directly beneath the star. Modern climate models of tidally locked exoplanets frequently predict the formation of this substellar superstorm. It would be the planet's atmospheric navel, the central engine of the global heat distribution system. Imagine a hurricane on Earth, but scale it up to the size of a continent, or even larger. The eye of the storm would be a region of strangely calm descending air directly under the star, but surrounding this eye would be a colossal wall of rising air and cloud, spinning with ferocious velocity. The winds in this storm wall would be supersonic, driven by the immense energy differential between the heated surface and the cold upper atmosphere. This superstorm would act like a colossal chimney, venting the planet's excess heat into the upper atmosphere. The hot air, once it reaches a high altitude, would then flow outwards in a radial pattern, like water spraying from a fountainhead. These outflowing winds would form the basis of the global jet streams that carry heat to the night side. The weather of the entire planet would be dictated by the behavior of this one monstrous storm. The clouds in this storm would be spectacular. They would likely not be made of water, which would have long since boiled away. They could be made of more refractory materials, like vaporized rock and silicate minerals. Clouds of quartz or corundum could condense in the cooler upper regions of the storm, creating glittering crystalline thunderheads that tower hundreds of kilometers high. From the ground, standing near the edge of this storm, the view would be terrifying. A permanent spinning wall of cloud would dominate the horizon, its top lost in the hazy orange sky. The roar of the wind would be a constant deafening thunder. The ground would tremble with the storm's energy. It is a feature so large and so powerful that it moves beyond meteorology and becomes a kind of atmospheric geology. It is a storm as permanent as a mountain range. a testament to the extreme forces at play when a world is chained to its star. The existence of this storm has a profound implication. It means the day side is not a quiet furnace, but a dynamic, violent engine, constantly churning and exporting its energy to the hidden hemisphere of night. The hot, fast winds flowing from the dayside superstorm carry a precious cargo: heat and water vapor. As this air journeys into the eternal darkness of the night side, it begins a process of catastrophic cooling. It is radiating its heat away into the cold, black emptiness of space. The temperature plummets. This triggers a phenomenon known as atmospheric collapse, or freeze out. As the air cools, the gases within it can no longer remain in their vapor state. They begin to condense and freeze, precipitating out of the atmosphere and falling to the surface as snow. The first gas to freeze out would be water. As the wind crosses the terminator line, any water vapor it holds would instantly crystallize and fall. But as the wind continues its journey deeper into the night, the temperature drops even further. On a planet with a carbon dioxide atmosphere, like a rocky world in the habitable zone, the temperature will eventually drop below -78 degrees Celsius, or -109 degrees Fahrenheit. This is the freezing point of carbon dioxide. The CO2 gas itself will begin to turn into a fine, dry ice snow. Imagine a blizzard that never ends, covering an entire hemisphere. This is not water snow, but a constant, silent fall of frozen atmosphere. This process actively removes gas from the atmosphere, causing the surface pressure on the night side to drop significantly. This pressure drop creates an even stronger pressure gradient across the planet, which in turn accelerates the winds, pulling even more air from the day side to replace what was lost. It is a runaway feedback loop. The colder it gets, the more the atmosphere freezes, and the faster the winds blow to fill the void. Over millions of years, this great freeze-out would build up truly colossal ice sheets on the night side. These would not be just water ice glaciers. They would be vast, layered deposits of water ice, carbon dioxide ice, and potentially even nitrogen ice if the planet gets cold enough. These glaciers could grow to be 10, 20, or even 50 kilometers thick, burying the night-side topography completely under a planetary ice cap. The weight of this much ice is almost unimaginable. It would exert so much pressure on the crust below that it could trigger geological activity. The immense weight could depress the crust, cause fault lines to shift, and even induce a form of cryovolcanism, where slushy, semi-liquid water erupts from beneath the ice sheet. The night side is not a dead, static place. It is an active geological region, shaped and crushed by the weight of its own frozen sky. The atmosphere, born in the fire of the day side, comes here to the night side to die and be buried. The perpetual blizzards and the relentless freeze-out create a landscape on the night side that is dominated by a single substance, ice. But this is not a static, unchanging world of ice. It is a dynamic system, a world of glaciers so vast they make Earth's polar caps look like ice cubes. The sheer scale of these ice sheets means they would not sit still under their own colossal weight. They would begin to move, sculpting the hidden face of the planet over geological time. At the base of a glacier 50 kilometers thick, the pressure is immense. This pressure, combined with the faint geothermal heat flowing from the planet's core, could warm the bottom layer of the ice, enough to make it flow like a thick, viscous fluid. The entire ice sheet, a continent-sized slab of frozen gases, would begin to creep slowly across the surface. This is glacial flow, a process that carves and reshapes entire landscapes on Earth. As these planetary glaciers flow, they would grind against the bedrock beneath, carving deep valleys and fjords. They would pluck massive boulders from the ground and carry them for thousands of kilometers, depositing them in strange alien formations. The landscape of the night side would be a classic glacial topography, but on a scale that is difficult to comprehend. Imagine the Grand Canyon, but filled to the brim and carved out by a river of solid CO2 ice. The direction of this flow would be predictable. The ice is constantly being deposited at the coldest point, the antistellar point in the center of the night side. From there, the glaciers would flow outwards, downhill, towards the only source of heat, the terminator line. This creates a colossal, slow-moving conveyor belt. Frozen atmosphere falls as snow in the center of the night side, gets buried and compressed into glacial ice, flows for millions of years towards the twilight zone, and then, as it reaches the warmth of the terminator, it begins to melt and sublimate. At the edge of the terminator, the great glaciers would meet their end in a spectacular fashion. As they hit the region of permanent gentle sunlight, the ice would begin to turn directly back into gas in a process called sublimation. Great cliffs of ice, kilometers high, would constantly be fizzing and steaming, releasing their trapped gases back into the atmosphere. This gas would then get caught in the global winds and flow back towards the day side, to eventually be carried back to the night side to freeze again. It is a complete planet-spanning cycle, but one that operates on geological time. Meltwater from the base of these glaciers would form vast subglacial lakes, insulated from the cold by the ice above. These lakes of liquid water, kept liquid by pressure and geothermal heat, could be some of the most stable habitats on the entire planet, completely shielded from any radiation from the star. The night side is not just a tomb. It is a dynamic, evolving landscape, a world of moving mountains of ice, hidden liquid oceans, and a slow, inexorable creep towards the distant, eternal dawn. From the surface of the night side, the sky is a masterpiece of cosmic clarity, a vista of unparalleled and terrifying beauty. With no sun to wash out the starlight, and an atmosphere that may be thin or non-existent in the upper layers, the universe is revealed in its purest form. It is a sky that has been lost to us on Earth, a sky that our earliest ancestors might have glimpsed before the advent of fire and city lights. Looking straight up from the antistellar point, the center of the dark hemisphere, you would see the celestial sphere in a way no human ever has. The stars would not twinkle. Twinkling, or scintillation, is an artifact of viewing stars through a thick, turbulent atmosphere. Here, in the thin, frigid air, the stars would be sharp, steady, unwavering points of light, like tiny diamonds pinned to a black velvet cloth. Their colors would be more vivid than we can imagine, from the fiery orange of red giants to the brilliant blue-white of young, massive stars. The Milky Way, our own galaxy, would dominate the view. It would not be the faint, cloudy band we see from a dark site on Earth. It would be a colossal, blazing river of light, a celestial architecture of such brilliance and complexity. It would seem almost three-dimensional. You could clearly distinguish the great dust lanes, not as dark patches but as intricate swirling voids that snake through the stellar river, obscuring the galactic core behind them. The core itself would be a luminous, glowing heart, casting a faint, ghostly light, a Gijan shine of starlight, that would be the brightest feature in the sky. This faint glow would be enough to navigate by, reflecting softly off the vast plains of ice. But the sky might not be entirely peaceful. Tidally locked planets around red dwarfs are often bathed in intense stellar winds and magnetic fields. If the planet has managed to retain its own magnetic field, this interaction would create auroras of an unimaginable scale. On Earth, the aurora borealis and australis are confined to the polar regions. On a tidally locked world, the magnetic field interaction is different. The stellar wind might be funneled into vast, glowing curtains of light that dance perpetually across the entire night-side sky. These auroras wouldn't just be green and red. Depending on the atmospheric composition, they could be brilliant blues from nitrogen or deep crimsons from hydrogen, painting the frozen landscape in ethereal, shifting colors. Imagine standing on a plain of solid nitrogen ice, under a sky dominated by the blazing arc of the Milky Way, while silent, continent-sized sheets of purple and blue light ripple overhead. It is a vision of profound, silent, and cold majesty. This is the sky of the night side, a constant and eternal reminder of the galaxy that the planet drifts through, a cosmic ceiling on a planetary prison of ice. What would it sound like, standing on the frozen plains of the night side? Our intuitive answer is silence, and in many ways that would be true. The atmosphere here is thin and incredibly cold. Sound, which is just a pressure wave traveling through a medium, propagates poorly in thin, cold air. The high-pitched, sharp sounds we are used to would be muted, absorbed by the stillness almost instantly. A normal conversation would be impossible. You would need to shout to be heard from just a few feet away. The world would be wrapped in a profound, deep quiet. But silence is never absolute. The planet itself would have a voice, though it would speak in a register far below the range of human hearing. The colossal glaciers, constantly under stress from their own weight and the slow, inexorable pull of gravity, would be groaning and cracking. This would not be the sharp, cracking sound of ice on a frozen lake. It would be a deep, resonant, infrasonic rumble, a vibration you would feel in your bones more than you would hear with your ears. The entire ice sheet would be humming with a low-frequency song, the sound of a continent of ice in slow, perpetual motion. As you move closer to the terminator line, the soundscape would begin to change. Here at the edge of the great glaciers, where the faint light of the star begins to warm the ice, you would hear a new sound, the gentle hiss of sublimation. Trillions of tons of frozen gas, cliff faces of ice kilometers high, would be turning directly back into vapor. It would be a sound like a billion whispers, a constant, faint, sibilant sigh as the atmosphere returns to itself. And then there is the wind. The great heat engine of the planet drives a perpetual planet-girdling wind from the cold side to the hot side. In the upper atmosphere, this wind is supersonic, but at the surface, it would be a different beast. It would be a dense, heavy, cold wind, flowing like a river of unseen fluid, with little to no surface features to break it up in the vast ice plains. The wind would be largely free of turbulence. It would not be a howling gale, but a constant, powerful, and almost silent pressure. The sound it would make would be another deep infrasonic hum, the fundamental frequency of the planet's breath. The most dramatic sounds would be geological. If cryovolcanism is active, the eruption of a slushy water-ammonia mixture from beneath the ice would be a cataclysmic event. It would create a deep, shuddering roar that would travel for thousands of kilometers through the solid ice sheet, a seismic drumbeat announcing a rare moment of violence in this otherwise quiet world. The night side is a world of silence, yes, but it is a silence filled with the deep, slow, powerful sounds of a planet's geology and atmosphere at work, a symphony played on an instrument the size of a world, in a key too low for us to hear. For all the potential havens that might exist in the twilight zone of a tidally locked world, there is a looming existential threat that comes from the very star that gives it life. The red dwarf stars that host most of these planets are not the calm, stable suns we are used to. They are small, tempestuous, and prone to fits of extreme violence, especially in their youth. The greatest danger they pose is the superflare. A flare is a sudden, intense burst of radiation caused by a magnetic disturbance on a star's surface. Our own sun produces flares, but those from a young red dwarf can be thousands or even tens of thousands of times more powerful. A single superflare can release as much energy as 100 billion 1 megaton atomic bombs. For a planet orbiting in close proximity, such an event would be a cataclysm. Imagine the sky in the twilight zone. The dim red star hangs motionless on the horizon. Suddenly, and without warning, it brightens by a factor of 1,000. For several minutes, it blazes with an incandescent white light, bathing the landscape in a harsh alien glare. This is the visible light component of the flare, but the real danger is invisible. The flare unleashes a ferocious wave of high-energy X-rays and charged particles that washes over the planet at nearly the speed of light. If the planet has a magnetic field, it will be slammed by this coronal mass ejection. The auroras on the night side would erupt into a violent, planet-spanning frenzy of light as the magnetic field is overloaded. But a magnetic field can only offer so much protection. A powerful flare can literally strip a planet's atmosphere away, eroding it over time like a cosmic sandblaster. A world that might have started with a thick, protective atmosphere could be rendered an airless, barren rock after a few 100 million years of repeated flaring from its parent star. Even if the atmosphere survives, the radiation poses a deadly threat to any life on the surface. The burst of X-rays would be powerful enough to sterilize the day side and the terminator zone, destroying complex organic molecules and causing lethal mutations in any organisms not sheltered deep underground or underwater. Life's only true refuge would be the deep subglacial oceans of the night side, shielded by kilometers of ice from the star's fury. This threat presents a profound paradox. The very stars that are most numerous in the galaxy, the ones that offer the most potential real estate for planets in the habitable zone, are also the most violent and dangerous. For life to arise and survive on a tidally locked world, it needs a perfect storm of fortunate circumstances, a thick, resilient atmosphere, a strong, protective magnetic field, and a parent star that has aged out of its most violent youthful phase and settled into a calmer middle age. The twilight zone may be a potential Eden, but it is an Eden that exists under the constant threat of annihilation from its own sun. Water is the lifeblood of a planet, the solvent that makes the chemistry of life possible. On a tidally locked world, the fate of water is a dramatic story of planetary migration, deep freezes, and potential sequestration. The global climate is effectively a colossal machine for moving water from the day side to the night side, and the planet's long-term habitability depends entirely on whether any of that water can be returned. Let's assume a planet starts with a significant inventory of water, perhaps in vast oceans covering much of its surface. On the day side, under the relentless glare of the star, this water would evaporate at a tremendous rate, creating a thick, humid atmosphere. This water vapor would then be transported by the planet-spanning winds toward the cold night side. As soon as the air crosses the terminator line and begins to cool, this water vapor will condense and freeze, falling as snow. This process acts as a planetary water trap. Over millions of years, it could physically transport the entire planet's surface water from the day side and deposit it as a gigantic ice cap on the night side. The day side would be left bone dry, a desiccated desert, while the night side would hold all the world's water locked away in a glacier kilometers thick. This is one of the great threats to habitability on tidally locked worlds. They have a built-in mechanism for hiding their water away in a planetary freezer. How could a planet escape this fate? There needs to be a mechanism for returning the water from the night side back to the warmer terminator zone. One possibility is glacial flow. As we've explored, the immense weight of the ice cap would cause it to flow slowly outwards from the center of the night side. This could act as a conveyor belt, physically transporting the ice back to the terminator where it can melt or sublimate, replenishing the atmosphere with water vapor. However, this process is incredibly slow, operating on geological timescales, and it might not be efficient enough to counteract the rapid freezing. The more dynamic mechanism would be geothermal activity. If the planet is geologically active, heat from its core could create subglacial volcanoes on the night side. An eruption beneath the ice sheet would melt vast quantities of ice, creating enormous subglacial lakes and potentially triggering catastrophic outburst floods, known as jokolops on Earth. These floods would send torrents of liquid water flowing from under the ice out into the terminator zone, creating temporary rivers and seas. The most stable solution would be a thick, insulating atmosphere. If the atmosphere is dense enough, the heat engine effect will be powerful enough to keep the surface temperatures on the night side from dropping to the point where water freezes so efficiently. A thick atmosphere acts like a planetary blanket, moderating the extremes and allowing for a more stable global water cycle. The ultimate question of whether a tidally locked planet can remain wet and habitable over billions of years comes down to this delicate balance between the atmospheric heat transport and the efficiency of the night-side water trap. If life can take hold in the terminator zone, and if it can survive the fury of its star to evolve intelligence, what kind of civilization would it build? A society born on a tidally locked world would be fundamentally different from our own, their entire culture shaped by the unchanging landscape of eternal twilight. Their cities would not be sprawling, open metropolises. They would be compact, defensive structures, designed to withstand the relentless, unidirectional wind. We can imagine cities nestled in the lee side of mountain ranges, using the rock itself as a shield, or perhaps they would build partially subterranean structures, digging into the ground to escape the perpetual gale. Architecture would be a study in aerodynamics. Buildings would be low, rounded, and reinforced on the windward side that faces the cold night. Energy would be the primary driver of their technology. They could draw power from the wind, which is a constant and limitless resource. Vast arrays of turbines could be built in the windiest corridors, generating power for their civilization. Geothermal energy would also be a crucial resource, especially if the terminator zone is geologically active, with hot springs and volcanic vents. And of course, there is solar power. The star never moves, so solar panels would not need to track across the sky. They could be fixed in place, permanently aimed at the star on the horizon, providing a steady, reliable source of energy, day in and day out, because there is no day out. Their conception of time would be alien to us. Without a day-night cycle, the fundamental rhythm of life on Earth is absent. How would they measure time? Perhaps by the slow, subtle color shifts in the sky as their star undergoes its own cycles of activity. Or maybe they would use a purely mechanical or atomic clock, divorcing the concept of time from any celestial movement. Their calendar would not be based on seasons in the same way ours is, as the climate in any one location would be remarkably stable year-round. Their psychology and mythology would be fascinating. The star on the horizon would be a central divine figure. The day side, which they could never visit, would be a mythical land of fire, a heaven or a hell. The night side would be a place of terrifying cold and darkness, a land of monsters or lost souls. Their entire cosmology would be a duality of light and dark, hot and cold, embodied in the physical reality of their world. Exploration for them would not mean sailing across an ocean to discover new continents, but a perilous journey east into the heat, or a terrifying expedition west into the ice. Their entire civilization would be a thin, fragile ring of life, a testament to the ingenuity required to thrive on the edge of night. These strange, divided worlds are not just theoretical constructs. They are real, and they are out there, orbiting distant stars by the billions. But how can we possibly study them from light years away? How can we know if one side is hot and the other is cold? The answer lies in detecting the faint light of the planet itself and watching how it changes over time, a technique known as phase curve analysis. When we discover an exoplanet using the transit method, where we see the star's light dip as the planet passes in front of it, we can often continue to monitor that star's light very precisely. As the planet orbits its star, we see different parts of its surface illuminated. When the planet is moving towards us from behind the star, we are seeing mostly its night side. As it comes around to pass in front of the star, we see more and more of its day side. The total amount of light we receive from the system will change slightly depending on which face of the planet is turned towards us. The day side of a tidally locked planet is hot, and hot things glow, primarily in infrared light. The night side is cold and emits almost no light at all. By measuring the tiny variations in the infrared light coming from the system as the planet orbits, we can map the temperature difference between the two hemispheres. If we see the system's light get brighter as the planet's day side swings into view and dimmer as it swings away, we have direct evidence of a hot side and a cold side. This is the signature of a tidally locked world. This technique is incredibly challenging. The light from the planet is millions or even billions of times fainter than the light from its star. It's like trying to detect the heat from a candle flame next to a searchlight from 100 miles away. But our technology is getting there. The Spitzer Space Telescope was a pioneer in this field, and now the James Webb Space Telescope is revolutionizing it. With its incredible sensitivity and powerful spectrographs, JWST can not only detect these phase curves, but can also analyze the chemical composition of the planet's atmosphere at different points in its orbit. By looking at the spectrum of light just before the planet disappears behind the star and comparing it to the spectrum as it emerges, we can search for the chemical fingerprints of molecules like water, methane, and carbon dioxide. This allows us to test our models directly. Can we see evidence of water vapor being transported to the night side? Can we see the chemical signature of rock clouds on the day side? We are no longer just imagining these worlds. We are beginning to measure them, to take their temperature, and to read the secrets hidden in their faint, distant light. Our journey into the eternal night has shown us that half a world is not half a planet. It is a universe of its own, with its own rules, its own climate, and its own potential for life. We have traveled from the gravitational shackle that binds these worlds to their stars, to the two dueling faces of fire and ice they are forced to wear. We have seen how a thin atmosphere can become a great heat engine, creating perpetual winds and a narrow, habitable ring of twilight at the terminator. We have plunged into the darkness of the night side, a realm not of dead stillness, but of dynamic moving glaciers, silent auroral storms, and a landscape sculpted by the slow, inexorable creep of ice. We have faced the existential threat of a violent red sun and considered the delicate balance of a planetary water cycle that constantly threatens to hide its most precious resource in a frozen vault. The tidally locked planet represents a fundamental shift in our search for life. For so long, we have searched for copies of Earth, for worlds with gentle rotations and stable climates. But the universe may be telling us that this is the wrong place to look. The most common homes for life may not be these idyllic exceptions, but the strange, violent, and divided worlds that orbit the most common stars. Life, if it exists out there, may not be basking under a friendly yellow sun. It may be huddled in the permanent twilight of a red dwarf, its entire existence adapted to a world of constant wind and a sky where the sun never moves. To find it, we must learn to look in the shadows. The night sides of these worlds are a profound reminder that our experience of a planet is just one of an infinite variety of possibilities, and that the cosmos is filled with more wonders and more potential homes than we have ever dared to imagine. The great dark ocean of the galaxy is full of these hidden shores, waiting for the light of our science to finally reach them.